So when it goes from here to the lowest position, what's the angular speed here? So this question, what we need to use is the conservation of the energy. Okay. First thing is the same. We need to calculate the moment of inertia for the whole system, and then we know here is 0.5, here is 0.8. That's the R, right? For this object, m times 0.5 squared, and for this one is m times 0.8 squared. Here you are clear, okay? So we'll calculate, that would be 0.89 times m. Okay, that's the moment of inertia for the whole system. And the next thing is, what's the energy here? It's the potential energy. When it goes from here to here, this object dropped 0.5. You know, here is 0.5 meter, right? And this object goes from here to here, it drops 0.8 meter. The loss of energy, the potential energy, this object lost is mg times mgh, right? Times 0.5 meter. And the energy lost for this guy will be mg times 0.8 meter. Okay. So that's the energy they lost. But what they got is they got an angular velocity for this whole system, which will give you an energy 1/2 I times angular velocity squared, right? So the potential energy convert to the angular velocity. So using these, we know I right now, 89 times m, and then the mass you will be able to cancel, right? And then you will be able to calculate. So here what you got is 0.5 g, 0.8 g is 1.3 g is equal to is 1/2 of this will be 445. Okay, times the angular velocity squared. And you know g is 9.8. Then you just need to divide and then square root. You will got is 5.35. So the correct answer will be B.
For the potential energy, we supposed to add them or we subtract? You said what's the loss?
The loss of the
So wouldn't it be subtract? For the potential energy.
the loss of this energy, you know, is mgh.
I know it's MGA, MGH, but
Those energy convert to the angular, the circular movement.
but we
energy,
add
right?
them. We add both energies, or we subtract
Yeah,
them.
we add them because this object and this object, both of them lost this energy, right?
Okay. Okay.
And then you convert both energy to, they both contribute to the angular movement,
Yeah.
right? So you just need to draw this and to see, oh, this one dropped to here, this one dropped to here, and then both of these loss of energy contribute to the circular movement. And then number 12. A uniform rod is 2 meters long and it's 1.5 kilogram. A rod is, the rod, there is a axis in one end. And then if you release, it will go like this, right? The rod is released from rest in a horizontal position. What is the angular speed of the rod when the rod make an angle? It go to here, and here is 30 degrees. Okay. The moment of inertia for the rod is 2 kilogram meter square. So we know these, we know the longs, we know the mass. The question is, what's the angular speed here? So from here to here, to solve this problem is also to use the conservation of the energy. From here to here, it lost some potential.